Hey, it's Warner, and this is the last section in Chapter 20. This is 20.10. This is LR circuits, and so to get an idea how inductors behave, we can study them in a DC circuit. This is with circuits that have batteries or other constant voltage power supplies, so it's not alternating back and forth. So this is an LR circuit. It's got an inductor in it, and it also has a resistor in it. So similar to a capacitor, remember, an inductor deals with current, capacitors deal with charge, and they store a potential. The inductor is assumed to be ideal. Its windings have negligible resistance. So at time 0, the switch is closed. They want to know what is the subsequent current in the circuit after a period of time. So the current through the inductor just before the switch closed is 0. After it's closed, the current is initially 0. And then there's an instantaneous change in the current through an inductor would mean an instantaneous change in its energy. So an instantaneous change in energy means that the energy supplied is in 0 time. So nothing can supply infinite power, and therefore current through an inductor must always change continuously, never instantly. So if I have an inductor that I know is going to go from 0 all the way up to 2 amps, it won't do that instantaneously. It takes a little bit of time for that to happen. So there's got to be some sort of change in time there. That's current through an inductor. So the initial current is 0, so there's no voltage drop across the resistor. The magnitude of the induced EMF in the inductor is initially equal to the battery's EMF. So we know that the current is rising at an initial rate, so here's change in current over change in time, and that's equal to the EMF of the battery divided by the inductance in the inductor. As the current builds up, the voltage drop across the resistor increases. The induced EMF in the inductor gets smaller. So here we see that the EMF in the battery minus the EMF in the inductor minus IR, which is essentially the voltage in the circuit, is equal to 0. So the E in the battery is equal to EL plus IR. So you'll notice kind of how this makes its way through. Tau is a time constant, just like we had in in capacitors, but now we're going to have a time constant for a inductor. Since the voltage across an ideal inductor is the induced EMF, we can substitute the EMF and the inductor and make that equal to L times the change in current over the change in time. So here EB is equal to the inductance times the change in current over the change in time plus the current times the resistance. So the battery EMF is constant, it doesn't change. So as the current increases, the voltage drop across the resistor gets bigger and the induced EMF in the inductor gets smaller. So this would be for the resistor, this is for the inductor. The rate at which the current increases gets smaller. So you'll see it'll happen pretty quick and then it'll kind of tail off. Same thing happened when we did the when we looked at the magnetic field in a solenoid or in a slinky. You saw that it took a little bit of time for this to get up to the 2 amps that we used at first. And once again, we talked about that little time constant on the bottom. So after a very long time, the current does reach a very stable value, and since the current is no longer charging, there's no voltage drop in the inductor. So here we just have the final current is equal to the voltage in the battery over the resistance in the resistor. The current is a function of times IT is, and so here we have the final current times 1 minus e to the negative t, there's our time, over that time constant. And for an LR circuit, this would be L over R. In a capacitor circuit, we said it was different, and we'd have to go back to that to see that one. So the induced EMF as a function of time is basically the equation we see here. It's just EB times E to the negative t over tau. The LR circuit in which the current is initially 0 is analogous to charging an RC circuit. So in both cases, the device starts with no stored energy, and it does gain energy once you close that circuit with a switch. If I charge a capacitor, the charge eventually reaches a non-zero equilibrium value, and in the inductor, the current reaches a non-zero equilibrium value. So what about an LR circuit that is analogous to discharging an RC circuit? So once there's a steady current flowing the inductor and energy is stored in it, how can we stop the current, reclaim it? We could simply open the switch, but that is not a good way to do it. That attempt to suddenly stop the current would induce a huge EMF in the inductor, and sparks would complete the circuit, so you would actually see a spark jump across that. That would allow, so essentially, sparking just isn't good for the health of the switch. It'll burn that switch out. So instead, the better way to stop the current is if we're charging an inductor. So here we're charging the inductor. Here's our voltage source or our source of EMF in the battery. We have current flowing through the switch, goes through the resistor, through the inductor, and over time this charges. Basically picks up current and then kind of goes through. The best way to stop it is to allow it to continue through the circuit through a second resistor. So we can close switch 2 and open switch 1. And that would be a better way to discharge the inductor. Here are some connections between a capacitor and an inductor. Voltage proportional to charge, and for an inductor it's proportional to the rate of change of current. The current can charge discontinuously. Here in an inductor the voltage can, but what cannot change discontinuously is voltage in a capacitor. Current is the thing that happens in the inductor. Energy is stored as I squared versus in a capacitor we said was V squared. When the voltage is 0 and the current is non-zero, our potential energy here is 0 and here it's a maximum, and then vice versa for the other one. So when the current is 0 and the voltage is not, U is at a maximum here and potential here is at a 0. Energy stored is proportional to E squared, and in an inductor it's B squared. Time constant was RC, that is the resistance times the capacitance, and in an inductor the time constant is just L over R. And then charging a circuit, here's the equations that you have, and then discharging a circuit, we've got those same type of equations, and you notice how they look pretty similar as we go through. Here's a good example. We have a large electromagnet, has an inductance of 15 henries. The resistance of the windings is about 8.2 ohms. So we're going to treat this electromagnet as an ideal inductor in series with a resistor. I close the switch, 24 volt DC power supply is connected to the electromagnet. They want to know what is the current that's going to be in there, and then how long after closing the switch does it take for the current to reach 99% of its final value. When the current does reach its final value, there's no induced EMF. In an ideal inductor, in the figure therefore has no potential across it. The entire voltage of the power source is across the resistor. When it's at 99% of the value, it has about only 1% left to go. So here's our solution for the first part. We know that this EMF in the battery should be equal to the EMF in the inductor plus the current times the resistance in the resistor. So when EL is equal to 0, so when the EMF no longer is going through it, then we have our final current. That would be the EMF in the battery divided by the resistor, so it's about 2.9 amps. So pretty easy thing to solve for. For letter B, the factor e to the negative t over tau represents the fraction of the current still to build up. And so when it reaches 99%, we've got the 1 minus e negative t over tau, or we've got e negative t over tau times 0.01. So that 1% left. So you can use either equation that you want to. If we do the natural log then of this side and of this side, we get negative t over tau, and then we have the natural log of 0.01, and that's equal to negative 4.61. So here we went ahead and said that t is equal to negative tau times the natural log of 0.01. We said that tau was L over R times the natural log of 0.01, so we have negative 15 henries over 8.2 ohms times our negative 4.61 from the natural log of 0.01, and we end up with 8.4 seconds. So it takes about 8.4 seconds for the current to build up to about 99% of its final value. And that is the end of this chapter.